Let's begin by analyzing diffusion in binary mixtures of components 1 and 2. Let U1 and U2 represent the velocities of motion of components 1 and 2 in a laboratory fixed reference frame. U is the molar average mixture velocity. Since the chemical potential gradients are constrained by the Gibbs-Duhem relationships, only one of the chemical potential gradients is independent. The mole fractions sum to unity, and therefore there is only one independent measure of composition. In the Maxwell-Stefan formulation, the force acting per mole of species 1 is balanced by friction species 1 experiences in undergoing relative motion with respect to species 2. The frictional term must be proportional to the composition, and we take that proportionality to be represented by the mole fraction of component 2. The physical significance of the Maxwell-Stefan diffusivity, where we use the symbol D with a line through it, is that it represents an inverse drag coefficient. The force acting per mole of species 1 is a negative of the gradient of the chemical potential with the units newtons per mole. The Maxwell-Stefan equation can be reformulated in terms of the diffusion flux, which is defined as the flux with respect to the molar average reference velocity Vm is the molar volume of the mixture. Rather than use the chemical potential gradient as a driving force, it is convenient to define a thermodynamic correction factor given by this expression, which quantifies departure from ideality. Indeed, if the activity coefficient is unity, gamma is equal to unity. And the Maxwell-Stefan equations can be recast into the form flux of component 1 is proportional to the mole fraction gradient of component 1, and the constant of proportionality is the Maxwell-Stefan diffusivity times gamma. Therefore, in comparison with the Fick's law, we note that the Fick diffusivity equals the Maxwell-Stefan diffusivity times a correction factor that quantifies departures from thermodynamic idealities. Let us examine diffusion in the binary mixture of methanol and normal hexane at a temperature of 313 Kelvin. The Fick diffusivity is plotted here as a function of mole fraction of methanol. We note that the Fick diffusivity decreases by about an order of magnitude as composition of 0.5 is approached from either end. By dividing the Fick diffusivity by the thermodynamic correction factor gamma, we obtain the Maxwell-Stefan diffusivity, and that Maxwell-Stefan diffusivity is practically independent of composition. This is the persuasive advantage of using the Maxwell-Stefan formulation, because it shows a more predictable composition dependence than does the Fick diffusivity. Now let's try and understand this reduction in the Fick diffusivity value as shown by the experimental data. The mixture of methanol and hexane undergoes phase splitting at temperatures below about 308 Kelvin. The green line represents the binodal curve, which is defined by the minimum in the Gibbs free energy, say at 290. These are the 2 points here where the partial derivative of G with respect to the composition X1 is 0. Those are the points. So plotting the minima in the Gibbs free energy versus composition curves, we can construct the binodal curve. The red line represents a spinodal curve. These are points at which the thermodynamic correction factor is 0. This is the same as stating that the second derivative of G with respect to the mole fraction is 0. So those are the points representing the spinodal curve. Within the region, the mixture will undergo phase splitting. Say if we take a composition here of 0.5, subject to a small perturbation, the mixture will yield a hexane-rich phase and a methanol-rich phase. The area between the spinodal curve and the binodal curve is a metastable region. A different way of expressing the phase splitting phenomena is to say that the Fick diffusivity is negative in this region. Now, the sharp decrease in the Fick diffusivity is due to the fact that at this temperature 313, we are very close to the two-phase region. Now, the phase splitting in liquid mixtures occurs too quickly or too fast in order for us to follow the diffusion trajectories. The Maxwell-Stefan diffusivity for a binary liquid mixture follows a simple logarithmic interpolation formula called the Vignes formula, which is presented here. This logarithmic interpolation formula is a very good approximation for a wide variety of mixtures such as say methanol hexane, water acetone, ethanol water, and we see that the logarithmic interpolation formula provides a good estimate of the variation of the Maxwell-Stefan diffusivity as a function of mole fraction of the mixture. So the estimation procedure for the Fick diffusivity is as follows. The first thing is to appreciate that the Fick diffusivity is strongly composition dependent due to thermodynamic non-idealities. Correcting the Fick diffusivities for thermodynamic non-idealities results in a Maxwell-Stefan diffusivity, that shows a predictable composition dependence. Since the composition dependence of the Maxwell-Stefan diffusivity is predictable, the estimation of the Fick diffusivity may be made at any composition based on the infinite dilution values of the Maxwell-Stefan diffusivities at either end of the composition range. So these are the two diffusivity values of the Maxwell-Stefan diffusivity D12 at x1 tending to unity, which is this position, and this is the Maxwell-Stefan diffusivity at x2 tending to 1, which is at this point. So if you want to estimate the Fick diffusivity, we start with these infinite dilution values, and using the logarithmic interpolation formula, we estimate first the Maxwell-Stefan diffusivity, and then correcting the Maxwell-Stefan diffusivity for the thermodynamic correction factor, we arrive at the Fick diffusivity at that desired composition. The question arises, how do we estimate these infinite dilution diffusivity values? The most well-known expression for estimating the infinite dilution diffusivity values is the Wilke-Change correlation, and I present this correlation as equation 4.1.8 from my textbook, Multicomponent Mass Transfer, John Wiley, 1993. This is a correlation which is dimensional. In other words, the diffusivity values are in the units of square centimeters per second. It's a constant, 7.4 10 minus 8. Phi2 is the association factor for the solvent, 2.26 for water, 1.9 for methanol, 1.5 for ethanol, and 1 if the solvent is unassociated. M2 is the molar mass of the solvent in grams per mole. T is the temperature in Kelvin. Mu2 is the viscosity of the solvent in millipascal seconds. And V1 is the molar volume of the solute at its normal boiling point in the units of cubic centimeters per mole. The values of mu2, V1, Phi2, etc. are available in the book by Reed, Prausnitz, and Poling, The Properties of Gases and Liquids. So if we switch the subscripts around, we can determine the Maxwell-Stefan diffusivity for species 2, that is dilute in presence of a large amount of species 1, where all you have to do is to use the subscript 2 in place of subscript 1 and vice versa. Table 4.2 of my textbook published by John Wiley, 1993, lists other empirical correlations for the infinite dilution diffusivity values. So the prediction of the Fick diffusivity for any binary liquid mixture at a given composition is as follows. We estimate the infinite dilution values at the two ends of the composition range. We interpolate to determine the Maxwell-Stefan diffusivity using the Vignes interpolation formula. And the next step is to correct the Maxwell-Stefan diffusivity with a thermodynamic correction factor, determinable using NRTL or UNIQUAC models for thermodynamic non-idealities.